So here it is, issue 353 again, and that Hollowood function, which I thought might be an interesting little puzzle in itself, trying to derive that. So what does Chris say about it here? Get ready for this lovely example of an exciting and creative mathematics discovery that would only be possible with a teacher willing to nurture curiosity and a bright student eager to embrace stuff beyond the curriculum. And there's pictures of the two of them there. There's Tim, the teacher. Now, isn't that just a quintessential high school yearbook photograph? It's 1960 and he's 17 years old, and the photographer's waving a picture of Brenda Lee at him to get his attention. And then there's Derek, proudly wearing those Elton John glasses he got off eBay. And he's basking in the sun down at Saltcoats, California. Much like Saltcoats here, except you get to go home with all your possessions. There's the thing, the name Derek. You just don't see that very often. In all my years teaching, only I've had one pupil called Derek. Derek Doughty, nice boy. It's just not that common over here. It must be perceived differently over there. It must be more common over there, I think. But certainly here it's a little bit sort of cringe-worthy. And I can say that because that's my name. In fact, didn't that Ricky Gervais create that series where he was looking for a sort of simple, slow-witted character? And casting about for a name, what does he come up with? Derek. You just don't get heroes or romantic leads called Derek. You can't imagine a scene where the hero bursts in to save the day and he's called Derek. No, that's the one that comes in afterwards with the mop and the bucket to clean it up. No, it must be perceived differently over there. I remember there was a film, an animated film called The Swan Princess, and in it there was a hero called Prince Derek. And I remember thinking, nah, that just doesn't sound right, does it? Anyway, so here's the Hollowood function. I don't really want to spoil the surprise. You'll need to evaluate this function for all integer values of x from -10 to 9, for example, and you'll see why the Hollowood function, which Derek explained to me was created after considering properties of recurrence relations, is so cool. Well, it does have a limited range of application, and you can easily make a program that would do what it tries to do completely with a simple loop of concatenations. But whilst computer programs are good at doing what they do, at finding things that would take you a lifetime to find otherwise, at finding 3 10-digit Pythagorean triples that involve the digits from 0 to 9 and all their permutations, or the gazillionth digit of pi. Not that the gazillionth digit of pi, I think, adds anything necessarily to the elegance of that little symbol. The problem with a computer program is you're essentially a spectator in the process. Give that to me, human, and I will solve it for you. No, there's nothing quite as satisfying as coming up with an elegant little function that does it in a single step, something like this. Well, give it a try and see if it tickles your fancy the way it seems to have done Chris. Oh, matron. So here it is then, this Hollowood function, which of course, if you've tried it out, only actually operates properly within a limited range of -10 to 9, and also only on integers. But if you did try typing it in, you might have tried something like h of 7 and found it came up with 1, 2, 3, 4, 5, 6, 7. Or if you tried typing in a negative, like -8, but for -8 you'd have found it come up with 0.7654321. That's because this part here is really a sort of a collateral calculation. It's just like a byproduct of what happens in this part. Notice you're actually getting the 8 here, because it's just reversing those 10s. However, it fails as soon as you do something like h of 12. Because as soon as you do that, you get 1, 2, 3, 4, 5, 6, 7, 9, 0, 1, 2, 2, and it falls apart. But the first part here was, how could you arrive at that in the first place? Well, the pattern that you were trying to establish, you were trying to find this function, you were trying to find a function that would generate this. At 1 it would produce 1, for 2 it would produce 1, 2, at 3 it would produce 1, 2, 3, and so on. So the problem here is, how can you take these numbers and find a pattern in them that will simplify to an expression expressed just in terms of, I'll call it n instead of x, in terms of n. So it's going to take a bit of cooking with these numbers to see what you can do to them to reduce them. And usually the perfect number to do that, certainly in normal calculations in base 10, it would be the number 9. 9 would be like the halogen for that base 10, because it's just one short of it. So we can start the cooking by saying, just experimenting, dividing by 9 is going to give me remainders, which won't be 1 to 1. Multiplying by 9, what do you get for all of these? So you take the first one, you get a 9. This one, you've got 108. Multiplying this one, you've got 1107. A pattern starts to develop. 1106. Run 11104. 5. 111104. And so on. So that started to produce some semblance of order. So that first step, which was multiply by 9, has produced this. And then you just start to think, well, how can I get this into a simple expression that can be expressed in terms of n? Well, the first thing would be subtract this thing off at the end. So, as a second step, if I take away this bit at the end, now notice this bit at the end could be expressed in terms of n. When it's a 1, it's a 9. When it's a 2, it's an 8. That's going to be, you take away 10 minus the n. So if you subtract 10 minus n as a second step, and I'll just work with this one now, that'll take it down to 111100. That's looking better. You can now see that you can get that towards a power of 10 if first of all you divide it by 100. That'll take it down to 11111. Then multiply it by 9. Will take me up to 99999, and then finally add 1. And that'll take me to 100000, which is a power of 10. And for this one here, that's power 5, so that must be 10 to the n minus 1. So I've ended up with this. There's a sequence of steps I can go through that when I start with n will reduce it to this. Or you could express it this way. If I call that function f of n, I can get that to turn into 10 to the n minus 1 if I put these operations on them. If I put 1 on it, followed by 2, followed by 3, followed by 4, followed by 5. Which means I can get back to f of n by reversing those. So, I'll start reversing those operations then. Last thing I did was add 1, so I'll take away 1. Next thing I did was times 9, so I'll divide it by 9. The next thing I did was divide by 100, so I'll multiply that by 100. Next thing I did was subtract 10 minus n, so I'll add 10 minus n. And then the first thing I did was times 9, so I'll divide it by 9. How can we get that a bit neater? Well, multiply everything by 9, so that will just be 100 of 10 to the n minus 1 plus 9 times 10 minus n over the 81. Just have to squeeze this in at the bottom now, and then finally we've got, that's a power of 2, so that goes up to 10 to the n plus 1. That's minus 100 plus 90, so that's minus 10. Minus 9n, all over 81, and there you go. So just rearrange the order again. F of n is 10 to the n plus 1 minus 9n minus 10 over 81. It just took a little bit of cooking with the halogen. Now, even though that fails as soon as you get x equals 10 and so on, because it just starts folding itself, there is a way you could extend this to get a longer string of digits, or digit-like numbers, and that would be to use different bases, because this expression only used those characteristic things of base 10. It used the base itself, it used 9, and it used 1. Those are the only numbers that were used in its construction. In other words, it used the base, it used the unit, and it used the halogen, if you like. It used the base minus 1. So it should be possible to use this in any base to get longer strings. And that would be just to generalise it to say if I take any base at all, and I think I'll call that n this time, since I'm just going to put whole numbers into it effectively, because those decimal parts were really just a sort of a byproduct. It was like collateral calculations. It should be this then. So operating in any base at all would be, now in any base, the base number itself is always 1, 0. So base minus 1 would have to be, I just have to express it as 1 less than the base, but the unit's always the unit. So picking a particular base, I would have, it would still be 1, 0. Remember, this is all in this base now, that is still the base. That would be n plus 1, where n is the number in that base, minus, now the halogen, one number less than the base, so that would be 1, 0 minus 1, multiplying the number, minus the base, divided by, again, that was the halogen, 1 less than the base, squared. That should work for any base. So theoretically, if you wanted to go up to Z, for instance, if you wanted the string that went 1, 2, 3, 4, bob, 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 A, B, C, D, bob, 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 up to X, Y, Z, that should be the last digit in base 36. Then that should be obtained by doing base 36 and putting Z into it, which I can't do in my calculator. Or if I take a base 16, if I do this in base 16, I should be able to get 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, for instance, by putting C into a base 16 equivalent of that, which would still be 1, 0 in that base of C plus 1, which is D, minus, now, the number 1 less than the base in base 16 is F, so it would be F times C minus the base, over again 1 less than the base, that halogen, F squared. If I did that in base 16, I should get this, but I can't check it in my calculator because my calculator will only go up to 8 digits in base 16. So to check if it actually works, I could try this. I could try in base 16, but just go to 6. So that should be the base to the power 7 minus F times 6 minus the base over the base squared. Except my calculator won't do any of these algebraic operations like fractions and powers and so on. It'll only do simple add, subtract, multiply and divide in a different base because I've set it into base 16. But I can still try it. So 1, 0 to the power 7, you could either type that all in as 10, it's not 10, I meant 1, 0, but I'll probably just say that. You could keep doing that, but in the end, you know, it's just going to end up with 1 followed by the 7 zeros, and that's as big as it can cope with. Right, so far nowhere. What about this? Minus F times 6, so minus F times 6, and then minus the base 1, 0. What have we got so far? Will it do all that in one go? Oh, it has. 0, F, 9, 6. Now I can't do divide by F squared, so I'll have to do divide by F. And I get this. And divide by F again, divide by F. And bingo, 1, 2, 3, 4, 5, 6 as expected. I've got these leading zeros because it just does that in those base calculations. But that's as far as I can check it with my calculator, but I don't see any reason why that couldn't be the extended one in any base. Now, even though this fails once you get to 10 and beyond, 2-digit numbers and 3-digit numbers, it's fairly straightforward to get a reconciliation that'll work, but a reconciliation's got its limitations in that it only lets you step your way through it. So you could have a reconciliation just to try and generate it in the first place would be, because the basic idea was you multiply by 10, then you add on the number. So I'll just put this down just as an example to begin with, and then I'll adjust the plus ones and stuff like that to actually make it work. And of course we'd be starting off with u of 0 would equal 0, and I really want u of 1 to be 1, and u of 2 to be 1, 2, and u of 3 to be 1, 2, 3, and so on. So if u of 0 was 0 and I want u 1, then the first thing I think I'd have to do is to adjust this down so this actually read what I wanted. So if that's n, I'll adjust that to n minus 1. So is this sufficient to make it work? So if this is 0, 10 times 0 plus 1 is 1. If this is 1, 10 times 1 is 10 plus 2 is 2. So that's it there. That would be the reconciliation. But of course that would also fail once you got to U10, because it would fold on top of itself, because for U10 you'd only be multiplying by 10, which moves it one space along, but you want to fit 2 digits in there. So that means you'd want to switch to multiplying by 100 if it was a 2-digit number. And you'd want to switch to multiply by 1,000 if it was a 3-digit number. What you need is some little function that will tell you how many what to multiply by for any given number. And of course the number of digits in a number in base 10 is related to the power of 10, and of course log base 10 tells you what power you've got. Log base 10 of a number tells you what power of 10 produces it. So that log base 10 of 100 is obviously 2, so that log base 10 of a 2-digit number, like 75 for instance, will be 1 point something. Log base 10 of 1,000 would be 3. So log base 10 of a 3-digit number, 753, would be 2 point something. So log base 10 will give you 1 less for the integer part. So that means you can create a function, call it d of n, that tells you how many digits it's got. And that would be, you do log base 10 of the number, that gives you 1 less, plus a decimal part, add 1 onto it. Now you've got the number, plus a decimal part, and get rid of that decimal part by doing integer. So now we've got the general recurrence relation. U of n would be 10 to the power dn of un minus 1 plus n, where dn equals int of log base 10 of n plus 1. But then that's just a recurrence relation. That just lets you work out the next one once you've got the one before it. But it does generate the string of numbers, ascending numbers. So you could generate this same function here, I'll call it h, but I'm going to call it n this time, also by doing a summation. You could say, well, if you add up numbers from 1 to whatever the number n is, but again it's got a limitation, it will stop at 9 and then start to fold on itself. By doing this, you could say I want it to read 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on up to the number. But of course it'll be built up by, I haven't got these lined up at all. It'd be built up by this. In other words, 1 would have to get multiplied by 10 to the power 4 if it was a 5. 2 would have to get multiplied by 10 to the power 3 if it was a 5. So you could say for this one I'm going to have 10 to the power, and that'll be n minus r. So when r is 1 there's 4, when r is 2, if it's a 5 there's 3, and so on, times r, would have the same effect as this, that summation formula. Again, it stops though when you get to n equals 10, and then it starts to fold in itself because you're only multiplying by 10. Just a little quick check with that, just a simple one. What if it was 4? According to that, if it was 4, it would be, r equals 1 to 4 of 10 to the power 4 minus r times r. So that would be r equals 1 should be 10 to the 3 times 1, then r equals 2, 10 to the 2 times 2, r equals 3, 10 to the 1 times 3, r equals 4, 10 to the 0 times 4, and that of course would be 4, and the 30, and the 200, and the 1000, 1, 2, 3, 4. But at least that lets you say this. Here's a little identity. R equals 1 to n of 10 to the n minus r times r is equal to 10 to the x plus, n plus 1 minus 9n minus 10 all over 81 for all n. But how would you extend this? Because the problem here, although you can see it more explicitly here than there, is you're only multiplying by 10. You'd want that to jump up to 10 to the power 2 when you put in a 2-digit number. But of course here, since 1 to 9 would be the zone, it'd only be moving 1 at a time, and then it would have to start moving 2, so there'd be a combination of the two. So you'd have a summation plus another summation. But
Right, Derek, that's your dinner ready.
Okay, Mum, but I'm busy.
No, just leave it.
But I'm almost done.
That's what you always say, stuck away in that wee cupboard on your own for hours. That's why you don't have any friends.
Do you have friends?
No, you don't. Now, get out here now.
In a minute.
I'll switch off the lights.
Right, okay then.